What if the same invisible process that keeps a phone from overheating helps a car engine survive a freeway drive and lets your fridge work at all is the same thing, heat transfer. It sounds simple. Heat moves from hot to cold. But once you start looking closely, you realize heat transfer is one of the most useful forces in modern life. It decides whether machines last or fail, whether energy is wasted or recovered, whether food stays cold, computers stay fast, and buildings stay comfortable. In this video, we are going to look at the most useful real-world applications of heat transfer, from engines to electronics, and more importantly, why it works so well. Because once you understand the mechanism, you start seeing design everywhere. Let us start with engines. In a car engine, fuel burns at extremely high temperatures. That heat creates pressure, and that pressure pushes pistons to generate motion. But here is the problem. Too much heat destroys parts. So engineers use heat transfer in two ways. First, they remove excess heat using coolant systems, radiators, and airflow. The coolant absorbs heat from the engine block, then the radiator releases that heat into the air. That keeps the engine in the safe temperature range. Second, they actually manage heat to improve efficiency. If an engine stays too cold, fuel does not burn as cleanly. Too hot, and components wear out fast. So the whole system is really a balancing act, not just getting rid of heat, but controlling where it goes. A simple example. If your car starts overheating in traffic, but cools down when you drive, that is because airflow over the radiator increases heat transfer. More airflow means more heat leaves the system. Now let us move to electronics. This is one of the biggest modern applications of heat transfer. Phones, laptops, gaming consoles, servers, all of them generate heat, and heat is the enemy of performance. Why? Because as components get harder, electrical resistance rises, materials age faster, and chips may slow down to protect themselves. That is why computers use heat sinks, thermal paste, fans, and sometimes liquid cooling. The mechanism is pretty elegant. A heat sink is usually made from metal with high thermal conductivity, like aluminum or copper. Its job is to pull heat away from the chip quickly and spread it over a larger surface area. Then fans or airflow carry that heat away by convection. Thermal paste matters too. It fills microscopic air gaps between the chip and heat sink, and air is a poor conductor. So by replacing trapped air with paste, you make heat flow much more efficiently. A practical example, if your laptop gets hot and noisy, clean the vents. Dust blocks airflow, which reduces convection, traps heat, and forces the system to work harder. That is heat transfer in action. Another huge application is refrigeration and air conditioning. This is one of the most useful heat transfer systems ever invented. A fridge does not create cold. It removes heat from inside and dumps it outside. That happens through a refrigerant that absorbs heat as it evaporates, then releases heat as it condenses. This cycle moves heat from a cooler place to a warmer one, which sounds impossible until you realize the system is doing work the entire time. That is why the back of a fridge feels warm. It is literally releasing the heat it took from the food compartment. Heat transfer also shapes buildings. Insulation works by slowing heat flow. In winter, it keeps warmth inside. In summer, it keeps outdoor heat out. This is why materials matter. Foam, fiberglass, and double-pane windows all reduce conduction and convection. In simple terms, they trap air, and trapped air is a bad heat conductor. A useful example. If a house loses heat too quickly, it is not just uncomfortable, it costs money. Better insulation means less energy needed for heating and cooling. So heat transfer is not just a physics topic. It is the reason engines run, electronics survive, food stays fresh, and buildings use less energy. The amazing part is that we do not just fight heat, we design around it. We move it, trap it, spread it, and control it. And once you notice that, you start seeing heat transfer everywhere. In your laptop, in your car, in your kitchen, even in the walls around you. Because in the end, the ability to control heat is one of the most practical powers in engineering. From engines to electronics, the most useful applications of heat transfer is just one small part of heat transfer. If you are interested, our full free heat transfer course is linked in the description.